Hello, my name is Vitaly, and the topic of this video is how to design a broadband MRI detector which can cover several nuclei. We can do this by manipulating Q factor of the preamplifier decoupled coils. We all know from the circuit theory that a bandwidth of an RLC resonator depends on its Q factor. So by manipulating the loading of the resonator, we can spoil the Q factor and extend the bandwidth. The principle of spoiling the Q factor of an MRI detector is already used in so-called preamplifier decoupling. The typical setup is illustrated on this picture. The coil inductance is loaded by a low noise amplifier through a matching and decoupling network. The purpose of this network is to transform coil impedance to the optimal noise impedance of the amplifier, Zn opt, and at the same time to present large impedance, ideally infinite impedance Zin, to the terminals of the coil. This is the impedance which defines Q factor and consequently the bandwidth. For a given coil and an amplifier, Zin is predefined because the output impedance of the network Zout is fixed at Zn opt, shown here on the Smith chart. The noise circles on the chart can be plotted using the given equations which can be found in most RF electronics books. Now, instead of a conventional matching to the minimum noise figure, NF mean, we can choose to match for a larger noise figure, say 0.2 dB larger. This will result in infinite number of impedances, which are on the green colored noise circle on the chart. It also means that now there is an infinite range of impedances Zin, which can define the bandwidth. Following the considerations above about the Q factor of a resonator, we choose the largest Zin from the range. If we do so, the SNR bandwidth becomes larger, though the peak SNR is now 0.2 dB lower. In addition, the preamplifier decoupling becomes better. Here on the graph to the right, you can see the normalized current in the coil loop when it's power matched to minimum noise figure and 0.2 dB above the minimum. The decoupling level can actually be calculated analytically, and the resulting curve is shown here. As you can see, the more noise figure you sacrifice, the better preamplifier you can achieve. Following the same procedure, we have plotted SNR bandwidth versus noise figure degradation for all possible circuit topologies. From the theory in the referred here paper, it follows that you need at least 3 degrees of freedom to satisfy the matching and decoupling conditions. And there are 4 possible solutions. There are 2 for T-shaped networks. We call them T1 and T2 topologies, and 2 for pi networks, pi 1 and pi 2. One thing to note is that different topologies lead to different bandwidths, since the circuit is more complex than a simple RLC resonator. Circuit pi 1 also leads to widest SNR bandwidth among all solutions. That topology was chosen for experimental verification. On this slide, you can see the photograph of the fabricated coil, the table with the values of the components when matched to minimum noise figure and 0.2 dB above that value, as well as simulated versus measured coil performance. It's quite difficult to catch this 0.2 dB difference in measurements. And in addition to measurement uncertainties, the loss in the implemented inductors, L3, is considerable, which is the reason why the SNR bandwidth is actually lower than in the ideal case. To get closer to the ideal case, we introduced 1 more degree of freedom, the 4th element in the matching and decoupling network. The resulting topologies and corresponding component values are showing on this slide. From the graph on the bottom, you can see that in order to cover the Larmor frequencies of carbon, sodium, and xenon nuclei in 3 Tesla scanners, the bandwidth of 3.2 megahertz is required, and approximately 0.3 dB noise figure has to be sacrificed if we choose the network represented by this orange curve. The network was split for symmetry, and active decoupling network based on a PIN diode is co-integrated. On this slide, the decoupling measurements set up as well as simulations and measurements are shown. The measurements are done using overlapped loop probes connected to a vector network analyzer. And here you can see the comparison to earlier published reference coil designed for carbon imaging, which was also used in imaging experiments. As one can see, the bandwidth is considerably wider now. On the right is the photograph of the SNR measurement setup. To evaluate the SNR performance of the coil in the array, the SNR as a function of H2H distance to two identical neighbor coils at three frequencies of interest are recorded. Here we observe that the typical curves with SNR level recovery when the coils are critically overlapped. In conclusion, the bandwidth of an MRI detector can be extended by spoiling the Q factor of the resonator. If you want to know more details, you are welcome to contact me by this email.